Okay, hi everyone. Let's recall the some exposition that yesterday speak about it and one of the theorem is about this one square free monomial ideal is radical ideal. Radical ideals and the radical of A, radical I is equal to intersection P belong to mean I for a monomial ideal I. Is one of the theorem yesterday speak about it. And two, if I is a monomial ideal of R, ideal of R, then I has this presentation. Has this presentation where QI is equal to X I1 and XI K AK for I 1 to M. This theorem said that every monomial ideal has a presentation with this form, and QI is this form, in which QI is this form. Every monomial ideal has a presentation and with this form, and in which QI has a this form. QI is it QI is a unreducible irreducible, and the redundant presentation of this form is uniquely. And three, a monomial ideal I is reducible, irreducible if and only if up to permutation of variables I has this form: x1 a1 and xr ar. So the irreducible ideal is characterize where I is a positive for all I. And every irreducible ideal for every irreducible ideal ideal is primary. This is the final theorem yesterday proved. And so we continue the
Professor Mafi, when you
Yeah.
say every reducible ideal is primary,
Yes.
do you mean
Yes.
every irreducible monomial ideal is primary?
Yeah, yes, every irreducible monomial. Yes, yes, true.
Okay, thank you.
This is for all monomial, for all irreducible ideal, this is true. For all irreducible ideal is primary. If we are is Noetherian and I is a irreducible ideal, then we have the primary ideal.
Definitely.
But now I speak about the monomial ideals. But
correct.
this theorem for all irreducible ideals is true.
No,
Yeah.
I know. Thank you.
But the characterization is important. The I irreducible when I is this form. But in the general, the form of the irreducible ideal is not the noun, only definitions. But in the monomial is characterized. And so I want to define the primary decomposition. Define a presentation. A presentation of an ideal I as intersection I is equal QI where QI is a primary ideal. And yesterday defined the primary ideal. Is a primary ideal is called a primary decomposition. And a primary decomposition A primary decomposition is called irredundant. When irredundant primary decomposition. Decomposition if none of the QI can be omitted, in this intersection. And this is the first condition. And the second condition is as a associate prime QI for maybe associated primary QI is a PI is not equal to ASA QJ for all I is not equal to G. And this to be between 1 and R. And this two conditions.
One question, just for understand condition 1.
Yeah.
Condition 1 means precisely, as far as I understand, that the QI is not contained in the intersection of the remainder ones.
QI is yes, QI yes, but when we for the
Otherwise, you
primary,
can omit it.
for the primary decomposition, we will see the examples. Primary the sum of QI cannot be removed, but the radical ideal is equal.
Yes, yes, I know.
For radical ideal.
Because you have embedded primes.
Yeah, yeah. Maybe some of them the radical is equal, and so
Sure.
gather these ideals gather together, and so this ideal is a primary. Yeah. For example, if you I is equal to Q1, Q2, Q3, for example,
yes,
Q2 and Q3 has a P primary. The radical ideal, 2 ideal is a P. So this radical of Q1, Q2 is P. The radical of Q3 is P.
Yes.
So Q1, Q2, Q3 is a P primary.
Yes.
So then we have I, another name for this one.
Yes.
Another name Q. Yeah, this is the primary, the redundant primary decomposition of this one.
Yes, exactly.
Yeah,
because you have embedded things. Yes.
Yeah.
Thank you.
So let me write some facts in here. Facts. If I equal to intersection of QI 1 to M, where each QI is P primary. Then I is P primary. I is P primary. The radical ideal, this ideal is easy, the proof of it, because we say that the radical by using the definition, and we have this is a P primary. Intersection of P primary ideal is P primary. And the fact of 2 if I is equal to I is an I redundant, is an I redundant primary decomposition. Composition of I, then QI, then primary composition of I, then the QI is called PI, primary decomposition, primary component. Primary component of I, and one has radical associated prime of A is equal to radical Q1, radical Q2, and radical QM. This is the P1 and PM. So the redundant primary decomposition give us the associated prime of ideal. For the finding of the associated prime ideal, it is enough find the decomposition primary decomposition, redundant primary decomposition of ideal. For the finding associated prime ideal, monomial ideals, it is enough finding the redundant primary decomposition of ideals. So for examples, let me the primary decomposition has one differences by irreducible. We know that every irreducible ideal is a primary, but every primary ideal is not irreducible. We have we will see some examples, and also for the decomposition of ideals, redundant primary decomposition has again difference with the irreducible decomposition. The irreducible decomposition is a unique, but this is not unique in general. But only the associated prime is unique. So note that in here. Note that the primary component belong to the minimal prime ideal the primary component belong to the minimal prime ideal of I are unique. Only some component of QI is a unique. The radical ideal is minimal prime ideal of I, and the other is not unique. Are uniquely determined. So examples. The ideal I is equal to x1 3, x2 3, 1 2 3 2, 1 2 3 2, and 2 3 2, and so has the following redundant presentation redundant presentation of a reducible ideal. And the primary irreducible ideal of this one is, as you see in the yesterday, has this presentation. X1, 3, X2, 3, X3, 2, intersection X1, X2, and X1, 2, and X2. This is the irreducible ideal. I has a presentation as irreducible ideal and satisfy in the condition of I. This presentation satisfy the condition, but cannot, don't satisfy in condition 2 because the radical of this ideal and this ideal is equal. So these are two ideal gather together. Do you hear me?
We can hear you. Yes.
Here, okay, but okay, yeah, okay. For this one, these two ideals consider since as of x1 and x2 is equal to x1 and x2. This is equal to as of x1, 2, and x2. And condition 2 is not hold. So set, as I mentioned before, set Q is equal to this one, x1 and x2, to intersection of x1, 2, and x2. And in here, this fact, if all qi has a p radical, all qi is p, and qi is primary, then I is p primary. So the intersection of these two, the radical of this p and radical of this ideal is x1 and x2. So the intersection as p primary is this ideal is a p primary, and this ideal is equal to as the intersection as before speak about the intersection of these ideals is equal to x1, 2, x2, and x1, x2. This intersection is equal to this because you know that the intersection of two ideals is equal to LCM U and V, U in GI and V in GG. By using this is we have intersection of these two ideals is equal this one. So this ideal is P primary. This ideal is x1, x2 primary. Primary. So so I has this presentation: x1, 3, x2, 3, and x3 to intersection x1, 2, x2, 4, and x1, x2. This is the redundant primary decomposition of A. This is the radical ideal is this ideal is irreducible, and so primary. This ideal is primary, and so this is the redundant, satisfying these two conditions. This one and this. So this is redundant. Primary decomposition. So note that the ideal x1, 2, x2, 2, and x1, x2, this ideal is primary, as you see in below, is primary, but it is not irreducible, because before characterize characterize the irreducible ideal, every irreducible ideal, and the same of the pure power, but this is has this element, and so this ideal is not irreducible, but it's not irreducible. Another example, let I equal x2 y and x y2. It's a very easy ideal. Then I has this presentation. I is equal to x1 y and x1 y and xy, and this one has this presentation. This one has this presentation. As before, we write here x2 y plus xy2, and so this one x2 intersection y plus xy2, and so this equal to x2 xy intersection y xy. This is cancel, and so we have y intersection. This one has x2 yx and yx2, and in here x2x x2xx intersection x2y. So I has this presentation x y and x2y. So this is a primary ideal, primary ideal. So primary ideal, this is the primary ideal. This is the radical ideal of this x, radical of the y, radical xy. And so satisfy in the definition, the 1 and 2. So this is a redundant primary decomposition of this ideal. And so this ideal and this ideal as are the radical of these two ideal is minimal, and so in another primary decomposition, this two ideal is repeated again. For example, this is another another primary decomposition, a redundant rather primary decomposition. So, yes. So here equal to what? Here x y. Oh, okay. One. Here yes, it's x. Here I have a mistake. Yes, x. This one y. This one x. Yes, and this here x2. So here x y2, and so here y2. I has a two primary decomposition, this one and this one, but the component of minimal, the component of the primary component of minimal prime ideal is repeated. Is the in all of the primary decomposition, this the ideal is repeated, but this one changes. And so the another example, it says that the primary decomposition the primary decomposition of a monomial ideal may not be unique. Be unique. So, and another example, the ideal of x2 and x1, 2 and x1, x2 has this let me write the primary decomposition of this. Find the primary decomposition of I x1, 2 on x1, x2. This ideal I x1, 2, x1, x2 is equal to x1, 2 plus x1, x2. This ideal is equal to x1 intersection x2. So we have x1 to x1 intersection x1 to x2. So this is equal to this one cancelled because belong to x1 intersection x1, 2 and x2. This is one primary decomposition. The another primary decomposition, x1 is as said, that's every minimal component of primary decomposition repeated. This one is repeated, but this one we can change this one. X12 and X1, X2, X2, T for all. T bigger than 2. And so I has infinity primary decomposition. The intersection of these two ideal is equal to this by LCM. By LCM is equal to this. And so this is the primary decomposition, radical of ideal. This one by equal to radical of this ideal. And so this is a primary decomposition, and this is a primary ideal. So I has infinity primary decomposition. Primary decomposition. So I has infinitely, infinitely a redundant primary decomposition. But for irreducible, this thing is not happen. So
Just a remark.
yes,
As you are saying, in general, you cannot guarantee that primary decompositions are unique if you don't put extra conditions. If you assume, well, there is as you know, there is a result by Ortiz saying that if you fix the nilpotency order of each primary component.
yes, the minimal component is fixed, cannot change. But this is the embedding.
Exactly.
This is minimal. This one is the embedded.
Exactly.
Yeah.
But what I said is that there is a result by Ortiz saying that if you have a primary decomposition, and if you have two primary decompositions, then
yes, has a two primary decomposition. Is the infinity primary decomposition, but the associated prime is fixed.
Exactly.
The associated prime is fixed. In here, if the associated prime is fixed, but the primary decomposition, the number of the primary decomposition, is fixed. But only the component is changed. The embedded component change.
Exactly.
Yes.
Thank you.
So corollary, the associate prime ideal, the associated prime ideals of a monomial ideal are monomial prime. Because the associate prime is a radical ideal. The associate prime ideal is a radical of monomial ideal, so it's a monomial prime. And another corollary, let I be a monomial ideal of R and P in S I associated prime I, then there exists a minimal monomial element U of R such that P is equal I U. Before, for every P in associated prime, P is equal I colon ideal of I and F. F is a polynomials. But in here, we can consider U is a monomials. It is enough for proof for monomials. Consider U is a monomials. This is a very, this gives a characterize the P. P is characterized by this one. Proof. Since P as how A, by definition, we have P is equal A F. This is a colon ideal. F belong to R. Exists. Then for each xi P is I F. From here, we have XIF in I. So I is a monomial ideal. Then for all P, all U in support of F, UXI, U belong to I because I is a monomials. I is a monomial by definition of monomials. Then xi in then xi for each xi, then P contain in I U for all U in support of F. So then P contain in I U belong to support of F. And for other side, on the other hand, if J belong to intersection of A, U belong to support of F, then we have G, U belong to I, this one, for all U in support of F. Then again, I is a monomial. Then we have G F belong to I. So G in I colon I with respect to F. This one is P. P. So P is equal to this, and so P is equal in intersection. But P is irreducible. P irreducible. Then we have P is equal to 1 after mu mono R. There exists. And I want to characterize the primary monomial ideas now. A monomial ideal I of R is primary if and only if is characterized after permutation of variables I is equal to x1 R1 and x of RR and x B1 and x BS, where I positive for all I between 1 and R, and this is the monomial element x as before. X B1 means x1, x2, and xr. This is one B, for example, T1, T2, and TR. So B1 is equal to these vectors. These vectors. All of them in here is a monomial element. This is the variables. X1 variable, XR variable, but X power P1 is monomial element, X power BS monomial elements. So, and union of 1 to S support of X BI, a subset of X1 and XR, and the support of XA, X power A is equal to X1, XI, such that I is positive. Very special. And the same of the support of the polynomials, and the support of monomials is equal to this one. the set of monomial variable, the set of variables, and has construction the monomial elements. So for the proof, this is from the right to the left is easy because prove that for the proof of the right to the left, the same of the proof of yesterday. Yesterday proof for the irreducible ideal is primary. The same of the proof is the same. So it is clear. It is clear as I is equal to x1 and xr, and so I is primary. The proof of this, the same of proof of irreducible ideal for when we prove that irreducible ideal is primary. So for the conversely, let I be a primary ideal. Primary ideal, then as a definition, as of A is equal to P. P is the prime ideal. P monomial prime ideal. So by permuting the variables, as we assume P is equal to x1 and xr are less and equal to m. Since radical of I is equal to P, then P power T contain is I. The T is exist as before prove that the same of this. So I is minimally generated by a set of the form x1 R1 and xr RR and x B1 and x BS, because I power T contain here. So all pure power contained here is a pure power. And so some of the monomial ideals, all of the monomial ideals in P power T contained here is. And so I don't have any pure power except x1 and xr, because I is a monomial ideals. monomial ideals. So suppose xj belong to support of x power pi. Then xj xbj xpi is equal to xj xc xc, where xc, x power c, is a monomial. Monomial element not in I, because we assume that B1 and Bs is minimal, and the smallest is not in I. So since I is primary, I is a primary, a power of, and so primary, it follows a power of xj. A power of xj is in I, thus xj belong to x1 and xr, because the radical ideal of this ideal is x1 and xr. So xj belong to the radical ideal here, and so here, so xj one of these variables, and so j between 1 and r. And this complete the proof. And so I has these forms, generated by this, and so if you have a this says that we do not have any other any other element generated. This is the generated of I. So is that and so we have this theorem tells us every power of prime ideal is primary. All power are power of monomial prime ideal, monomial prime ideal, monomial prime ideal is primary. Is primary, but this in general is not true. In general, is not true. Only for monomial primes or monomial prime ideals is a primary. But if you consider ideal is not from monomials, the power of monomial, the power of prime ideal is not necessary primary, is not necessary primary. So definitions, let I be an ideal of R an element F R is integral over I if there is an equation fk plus I1 fk minus 1 and ak minus 1 f plus ak equals 0. And so f is integral when we have these equations such that I belong to I want to this. So the set I bar is the integral closure of I is f such that f is integral over I. So is the integral closure of I. The integral closure is base ideals. And it is clear I contain is integral closure because every element of I has these equations. For example, f belong to I, then f minus f is 0. This is the is 1. This one is R1, and in this here is 0, and so I contain in integral closure contain in radical ideal, because when we have f in I bar, we have these equations, and so fk is equal A1 minus A1 fk minus 1 and k minus 1f plus rk. And when all of them in here in I, this one ak minus 1, this one ak, and this this summand contain in I. So fk in I, f in radical I. So we have this inequality. So I is integrally closed. I is integrally closed. Integrally closed if I is equal to a bar. For example, a square free monomial ideals is integrally closed. For example, a square free monomial ideal is integrally closed. Closed ideal is integrally closed ideal. And I is set, I is normal when all power of I is and R and all power of I, all powers of I are integrally closed. Closed. That is A power T integral is equal to T for all T bigger than 1. Is integrally closed. For example, maximal ideal, prime ideal is, we see that in primary prime ideal is integrally every power of every prime ideal is normal. For the proof of this prime ideal, we in the continuing we see that every prime ideal, every prime monomial ideal is polymatroid, and so and so is normal. And it's clear when we look the equations, it's clear the ideal of 0 integral is equal to radical 0. But in here, R is domain is equal to 0. R is domain, and so we have, but in general, we have the integral closure of 0 ideal is equal the radical ideal of 0. And so, fact, let I be a be a monomial ideal, then integral closure is a monomial ideal. Monomial ideal generated by all monomials U in R, monomials U in R for which there exists an integer k, such that uk in ak means a integral closure is equal to the set of U in R such that uk belongs to ik, there exists k in N. The integral closure is equal this set. This is a monomial ideal. So definition. An ideal I is called normally torsion free. Torsion free. If S of AK contain of S of A for all K. So example, if I is square free, and normally torsion free. Torsion free, normally torsion free, then S of A is equal to S of AK for all K. Proof. Since I is normally torsion free. Normally torsion free, then by definitions, S of AK contain S of A for all K. And I is on the other hand, I is square free. Then S of A is equal to mean I. And also, okay. And since radical of A is equal to radical I for alpha. Then it follows min I is equal to min K. Because the radical is equal, we have the min I is equal to min I power K. So min I S of A is equal min I is equal to min power I power K, and this one contained in S of AK. So then we have the equality, and so and this complete the proof. And fact this fact is two guys brought this fact. One of them Ratliff in 1976, and for monomial for ideas, and after that Brodmann in 1979 generalized for this ideal over Noetherian local ring, generalized for modules. For modules, the multiple of ideal in modules, but in here for ideals, In I1 to infinity is infinite, is proved by Ratliff, and Brodmann proved that S of S of I1 infinity N is G A I T and M infinity generated. This is finite. This proved by Ratliff, and this theorem, this nice theorem, proved by Brodmann in 1979.
Just a small remark. This the paper by Ratliff is by 1977.
This 77?
Yes, I check it through Machinet. Yes, 77.
No, I think 76 in Michigan Journal Math.
Yes, exactly. Yeah, 76.
Journal.
Yes, 76. You are right. Thank you.
Yeah,
you are right.
Six.
Sorry. Yes, 76.
Yeah, this is very nice paper. And this one in Proceeding of American Mathematics Society. The paper, this paper, very small, but this paper is big. But this one is 4 pages, but for generalized, but very nice paper. There exists an integer zero such that S of K AK is equal to S of AK power K plus 1 for all K bigger than or equal to K0. That means That means this union is AK A1 infinity is a finite set. Is a finite set. So in here the SO A power K 0 has another name. Is the SO K 0. Look to SO K 0 is equal to SO K 0 plus 1 and continuing. We set in here SO infinity. This one. SO infinity means SO AK 0. So SO K 0 is called the stable set. The stable set of the stable of associated prime of I. Associated primes of A and is denoted by SO infinity. And also the number of K0 has another name, the smallest. This is the set, but this one is a number, the smallest. The smallest K0 such that SOK equal SO K plus 1 for all K bigger than or equal to K0 is called the index. The index of S. The index of S and a stabilized index of S stability of A and denoted by S stable. So look, S infinity of A is equal to S of A naught such that S of AK is to set is no, this is enough, but for this one that's in here as a step I is equal to AM such that S of AM AK is equal to S of AK plus 1 for all K bigger than or equal to is the number. But this one is the set. That's infinite. So we have come back again to this fact of Ratliff and Bradman. I want to define the persistence, an ideal. Ideal I is set to satisfy the persistent property if S of A power K contain S of A power plus 1 for all K bigger than or equal to 1, and it is said to satisfy the strong resistant property if A power K plus 1 colon of this ideal is equal to AK for all K bigger than or equal to 1. In the continuing, you prove that every strong persistent property is a persistent property, but the persistent property is not necessarily a strong persistent property. We have counter examples. And Bradman for the proof. And when we study the paper of the Ratliff for the proof of stability by some use these conditions for K very big. For K very big, we have always this condition, and so the stability is happen. So lemma, let I be a monomial ideal of R and K plus 1, A is equal to AK for some K. For some K. Then S of AK contain of S of AK plus 1. If this equality happen in one K, then we have this one. In particular, if I satisfies the strong resistant property, the resistance property, then I satisfy the persistent property. Proof. We want to prove this one. Let P belong to S of AK, then S of AK, IK is equal to this one. AK plus 1. This colon ideal equal to AK. So S is equal, and so then P is equal to AK plus 1 colon of this ideal. U is a monomial ideal. Exists. Mon. So then we have this one. P is equal to AK plus 1, and this one is equal U stick in I. U AK A, and so this one is equal to, if I let I is equal to V1 and VR, then IK P is equal to AK plus 1, U V1 and U V R. This one is equal to intersection of 1 R AK plus 1 and U VI. So P is P is irreducible, then P irreducible, P irreducible, and so I is equal to AK plus 1 in colon ideals, colon U VI is set P, and so P in S of AK plus 1. Yes. And so S of K. Oh. So and so S of K contain of S of AK plus 1. And for the remaining of the proof, if for all K we have this one, so for all K is happens, and the remaining proof easily false. Easily false. So another fact, مقادم has two books. One of book lecture note. The name of the book asymptotic prime divisor. This book in 1983 has a nice theorem. Let I be an ideal, of R, then for all n bigger than m bigger than and equal 1, we have a n integral colon am is equal to a n minus m integral. If not that, if I is a normal ideal, is a normal ideal, then I has a strength resistance. A strength resistant property. Because when I normal, so by this fact, I n plus I k plus 1, I m is equal to 1, n is equal to k plus 1. This is equal to, by this definition, a k plus 1 minus 1 r3 integral. But this one, I is normal. So I normal is equal to ak plus 1 a, and r is normal is equal to ak. So is the ideal equal to this. So I is strength resistance. And lemma let I be a square free. A square free monomial ideals. Monomial ideal of R, then for all k bigger than equal to 1, S of A contain of S of AK. For the proof of this lemma, we want to use this, and also we want to using the minimal primes. For example, I want to, for the proof of this, we want to use, first we want to use this fact. or proof. I contain of A2. I is contain of AK plus 1 colon AK. This is easy because by elementary, one element in here, so on the another one element here, conclude that element is here. And so it is 1 equal to AK plus 1 integral AK by this fact, we have this one is equal to a integral, and this one is equal to A. So we have A is equal to AK plus 1 H. And again, by the same the proof of the here, S of A contain of S of AK plus 1 for all K bigger than and equal to 1. Another proof, mean S of A is equal to mean I, because I is square free. Mean I is equal to mean I K for all K type plus 1. This contain here S of K plus 1 for all K bigger than or equal to 1. And lemma that X is ideal generated by X1 and Xt and I be a monomial ideal. Monomial ideal of R such that Xi is not in support of for all I between 1 and 2. Then X power k plus 1 I colon Xi is ideal is equal to Xk I for all k bigger than or is equal to 1. The support of I is equal to union of this definition. U in GA. Support of I means this set. So proof. Suppose alpha in x bar plus 1 I this column ideal. And so alpha xi belong to x plus 1 I. And since this ideal, not that this one, x plus 1 is equal to, in here I writing x1. xi remove or cancel, and other than here xr plus xi r plus. And so when we these two ideal, we have this one. In the name of this ideal, for example, y is equal to y r plus 1, and xi x r plus r power k. This is the summoned out these two ideal. Power k plus 1 is equal to this. So since x r plus 1 I is equal to x y r plus 1 plus xi x r I, where y is equal to x1 and xi cancelled, and xi. Since this one is equal to this, and so it follows that alpha xi belong to this one. The ideal does not have a xi, and so, and also in the here xi is not the support of I. So but this ideal is a monomial, and so alpha xi belong to this one. And that, so alpha belong to x car I. This tell us x, so x car plus 1 I xi contain in x car I this, and the other side is easy, and it is easily since that x car I contain x car plus 1 I put on xi, because this ideal multiple xi always contain here. And so in contain this color ideal, and this complete the proof. And so we have the result. We have the result. Definition. Let I monomial ideal generated by U1 and UT be a monomial ideal. Ideal of R. We set degree I means the maximum of degree UI such that I between 1 and T. And before define the degree of monomial ideas. If you remember, so proposition let I be a monomial ideal of R such that degree I less than equal to 2, and if I is equal to x1 and xt plus I such that J is a monomial ideal of R with degree J is equal to 2 and xi is not in support of J for all I 1 and T, then I plus 1 is colon ideal of this is equal to K for all K bigger than or equal to 1. For the monomial ideal of degree less than and equal to, always we have the strength persistent property for all monomials. And so proof proof first we prove that AK plus 1 xi is equal to AK. for all k bigger than 1 and I between 1 and t. Since ik plus 1 by expand, we have this one. Expand out the I is equal to xj I plus 1 plus xjk. And so x k minus 1 g plus x k and x k plus 1 equal to this, where x is equal to x1 and x t. So it therefore follows a plus 1 this colon ideal is equal to this one jk, and jk and if you remember I plus g, I is equal to I xi plus g xi. So by using this this theorem, we have j colon xi, but j does not have a xi. Is equal to j colon xi is j, and so plus sigma I here j is equal to 1 plus 1 and x j xj j plus 1 minus j colon xi. So by previous lemma, we have this is equal to j plus 1 plus sigma j 1 plus 1 x j minus 1 j plus 1 minus j, and this one is equal to j plus 1 plus j k plus j x j k minus 1 plus x k x k j and x k plus 1 x k minus 1 x k. So this contain here, and we have this j k, and this ideal is I equal to ik equal to j plus x power k. This is ik. So and so we have this, and so we have ak plus 1 xi equal to ak. So and ak plus 1 xi contain aki I contain of ak plus 1 xi and prove that is this one is equal to ak, and ak contain here, so we have the equality. ak plus 1 a is equal to ak. It said that every right here, so every monomial ideal of degree less than equal to satisfy in a strong persistent property. So, and so we have, and also corollary, every monomial ideal of degree 2 less than or equal to satisfy in persistent property. I want to, this is all of sync and receive to ends. So if you have any questions or comments, send email for me, or if you have a question, I am here. You want to, you can ask any question you about these presentations.
Just one question.
Yeah.
Along the proof of the last result, where you have used that the degree of your monomial ideal is less or equal than 2? At which point exactly?
For we have example for degree of 3 is not true.
Yes, but no, I mean along the proof.
Yeah.
Along the proof you have done before in this part of the board, yes.
For
At which point you
degree
have
for degree of less than and equal to proof, we have the theorem.
Okay.
Yeah, we have the theorem. This is the theorem in here. Yeah, I generated by degree less than and 2. We prove that this is true.
Yes.
And for degree bigger than 2 is not true in general.
Okay.
Tomorrow I will write the counterexamples. For degree 3 is not true.
Okay, thank you.
Yeah. And thank you for your attention. And see you tomorrow.